A very warm welcome to you in the World Wide Web. I'm happy to meet you here to our sixth railway talk, and I would like to share my screen. Warm welcome to the sixth railway talk. My name is Bernhard Knoll. I'm Vice President of the Union of European Railway Engineering Associations, and I'm glad to be the moderator of this sixth railway talk today. We have a hopefully interesting topic. We want to talk about noise problems in marshalling yards, and I'm happy to announce that we have two beautiful speakers who will present this topic in a short presentation. It will be the first speaker, Mr. Manuel Gunacker from High Power Company, who is talking about solutions for noise reduction in the marshalling yards. And I'm also very happy to announce that Mr. Günther from FCP Company, a civil engineering company, will in the afterwards talk about ground-borne noise and vibration reduction in urban areas. I want to inform you that we will record this sixth railway talk so that everyone participating this meeting can have a look also afterwards in the next few days and review this meeting again and see it live on camera. I hope this is okay for everyone. And I would ask you please to reduce the noise and your micro if you do not speak, and also close your cameras so that we do not have problems with the data transfer during these presentations. Only the speakers will be visible for you, and I also would kindly ask you after each speech, I would kindly ask you to ask questions to the presenter. There you can make live questions, but if you do not want to speak live, you can also ask questions in the chat in this Teams link. So I will collect all your questions in the chat during the presentation, and afterwards I will summarize them and forward it to the presenter. And the same procedure for the second speaker, Mr. Ax. And afterwards, when we have finished these sessions, I will ask once again if there's still some open points you want to discuss with the presenters. So I hope if this short introduction is okay for you, I would like not to waste time. Let's start with the first presentation. I'm happy to introduce Mr. Manuel Gunacker from High Power Company to you. He will speak about solutions for noise reduction in marshalling yard. Mr. Gunacker was born in 1985. He is the CEO of High Power Company, and he has a master degree in telecommunications and media. He studied at the University of Applied Science in St. Pölten, and he started his career in 2011 in his company, starting developing some programming control unit tools and web portal tools, device manager, and since 2019 he is the CEO of High Power Company. In parallel, he joined some research projects, mainly on the assessment of acoustic impacts, especially in curved tracks, for the creation of special noise maps in Austria. There were a lot of partners, for example, University of Technology in Vienna, the Austrian Federal Railways, or Psi Acoustics. And the same partners took place in a project about top of rail lubrication or conditioning, especially in curved tracks, where the investigation was the focus on rail squealing. So I hope this short introduction gives you an impression of your first speaker, Mr. Gunacker, and then I would kindly ask him to start his presentation.
Thank you, Bernhard. So I will share my screen first. So yeah, hello and welcome. also from my side. I hope you can see it now.
Perfect.
Okay, super. Yeah, as Bernhard's already said, I'm one of the two CEOs of Highpower. Our headquarters is located in St. Pölten, Austria, which is about 30 minutes west of Vienna. Highpower was founded by my father, Richard, nearly 40 years ago. Starting out as a specialist for hydraulic fittings and hoses, we developed the first stationary rail lubrication system for the Viennese railway lines in 1987. From this time on, we have further focused our business on rail lubrication systems and have been developing and producing them ever since. We have 9 patents in this sector, and our distribution network includes over 20 partners around the world. Today, more than 1,400 rail lubrication systems have already been installed successfully in over 30 different countries. The stationary rail lubrication systems are mainly used to prevent wear and tear, as well as noise due to the rail-wheel interaction. Next, I would like to show you how our systems look and where they can be used. On this picture, you can see one of our stationary rail lubrication systems. This model is the one mainly used for the Austrian and German railways. You may notice that the system's cabinet is installed right on the catenary mast. Above that, the solar panel through which the system is powered is attached. Directly on the track, a sensor is installed, which detects the passing trains. Furthermore, the distribution strips are also installed there. Our lubrication systems are flexible and applicable in a lot of different environments for railways, metros, and trams. Thereby, we offer solutions with or without rail trailings. There are a variety of expandable models for the systems, depending on our clients' needs. As I was just saying, our rail lubrication systems can be used for a broad variety of challenges. However, the main objective always will be to reduce wear and tear and noise to an absolute minimum. Such areas of application are the rail flank or the top of the rail, as well as the guide rail or the beam rail brake. Further possible applications would be either the points of turnout, frog of turnout, check rails, or Dauteri data. In short, you name the problem, and we will find a solution individually tailored to our needs. Transitioning from there, my main topic today will be the possible noise problems and solution in marshalling yards. Therefore, I would like to briefly explain what marshalling yards are. The marshalling yard in this picture specifically is located in Hagen-Vorhalle, Germany. Basically, goods are transported from one location to another. This happens through freight trains, which are made up of individual wagons or groups of wagons. On the way to the destination, the freight trains can be split up again at railway junctions and resorted so that the wagons with the goods reach the destination at the end. Marshalling yards are used for this exact purpose of resorting. The structural composition of a standard marshalling yard can be rudely divided into 4 areas. First is the reception siding. The freight wagons are prepared in the reception siding. This is usually done with a shunting locomotive. Second is the marshalling hump. This is either a man-made hump or a natural gradient. The individual wagons or groups of wagons are pushed from the reception siding over the hump by the shunting locomotive and rolled down. Third is the sorting siding. The sorting siding consists of 10 to 40 tracks. The wagons roll down the marshalling hump to the target track. There, the wagons are sorted and arranged to the newly designated freight trains. And finally, the departure siding, through which the finished trains leave the marshalling yard, either for the designated destination or the next railway junction. Here we see the marshalling yard in Graz, in the south of Austria. The sorting siding of this yard consists of 16 tracks. The wagons are pushed from the reception siding, individually or in groups, over the marshalling hump using the shunting locomotive. To prevent the wagons from accelerating too much, there are various systems to slow them down. In the past, stop blocks or braking clubs were mostly used for this purpose. Since around 1920, these have been gradually replaced by a newer process, and now mechanical rail brakes are in use here. These include hydraulic, pneumatic, and Daute retarder rail brakes. The most common design is the beam rail brake. Although the speeds in the marshalling yards are significantly slower than on an open track, wear and tear as well as noise still constitute problems, mostly caused by the wheel-rail contact, as mentioned before. Mainly, bends tend to have two problematic areas: the rail flank on the outer rail of the track and the top of the rail on the inner rail of the track. Here in the left picture, the wheel of the train is pressed against the rail flank in the bend. The force and friction increases, and the wear on the wheel and rail flank does the same. And on the right picture, ripples appear on the inner rail in the bend, but also on the straight line. This can be caused by braking, irregular wheels, but also driving through bends. Wear and screeching also occur in switches on guide rails. The guide rails are touched by the side surfaces of the wheels. This causes the wheel to shear along the guide rail. Another problem consists in the rail brakes. The wheel is pinched when the downward rolling wagons are getting slowed down. This also results in shearing forces. Each and every one of these factors on either the rails or wheels results in a higher possibility of unnecessary wear and tear, as well as noise. Screeching is becoming more and more of an issue for the neighboring residents and therefore for the public as well. So appropriate steps need to be taken and solutions considered. How could these solutions look like? Sure, as all of you know, noise barriers are a common solution. We all know them and have seen them multiple times. They are available in the conventional designs, but also as low sound barriers. The neighbors are generally protected from noises like engine noise, rolling noise, and screeching. The striking disadvantage of noise is that all of our people who work near or directly on the track are not protected in the slightest, since they work within the bounds of the barriers and not outside them. Therefore, we must try to reduce or eliminate the noises directly at the source, preferably in a way that prevents it from appearing again. We can achieve this, for example, by lubricating or conditioning the rails. If we apply the right amount of lubricant in the right places, and above all, the right kind of lubricant, we can not only reduce wear and tear by a significant amount, but also reduce, maybe even eliminate noise problems altogether. Instead of noise barriers, a few other solutions are available, for example, top-of-rail conditioning, here on the right picture. During top-of-rail conditioning, a friction modifier is applied to the top of the rail. The passing trains distributes the friction modifier in the direction of travel. The friction modifier keeps the friction coefficient above a desired value and forms a protective layer between the wheel and rail to reduce or even prevent screeching. Furthermore, top-of-rail wear and ripple formation are reduced. Guide rails in switch areas can or should also be lubricated, which leads me to my next example. A lubricant is applied to the front surface of the guide rail via holes in the guide rail or via distribution elements. The lubricant reduces the friction coefficient as close as possible to zero in order to reduce wear and also screeching. As a final point, another possible course of action would be to work on the rail brakes, as the loudest noises can occur during braking. A friction modifier is applied here as well, which forms a protective layer between the brake beam and the wheel side surfaces. The friction coefficient is kept in order to ensure continued braking, just like it happened during top-of-rail conditioning. Now I would like to take a closer look at the rail brakes themselves. As I mentioned before, most marshalling yards today use mechanical rail brakes in form of beam rail brakes. This picture shows a rail brake system in Graz, Austria. What you can see here is a hydraulic double-sided beam rail brake. On the right behind the mast, we see the technical house for the rail brake. The rail brake is installed at the end of the marshalling hump in front of the sorting siding. To slow the downward rolling wagons down to the correct speed, various sensors are installed in front of the rail brake in the rolling direction. These sensors measure the weight using strain gauges and speed. Furthermore, the distance to the destination on the target track is considered so that the wagons stop at the correct position in sorting siding. To do this, the brake beams are pressed laterally, inside and outside, onto the wheel side surfaces. This pinches the wheel and creates noise. This picture shows the individual elements of the brake beams. If a friction modifier is now applied between these brake beams and the wheel side surfaces, the screeching can be reduced or prevented. It is vital to ensure that to keep the friction coefficient so that the braking is still guaranteed, as in the case with the top of rail conditioning. For this, we use a friction modifier. This is a special medium with a high solid lubricant content, which keeps the friction coefficient in the desired range after application. To ensure that the desired amount of friction modifier gets to the right place on the wheel or brake beam, a system was developed together with the ÖBB and WWG, the BrakeMaster BR25. The BrakeMaster BR25 is installed in front of the rail brake in the rolling direction. Next to the track is a system cabinet with the system technology and friction modifier. The distribution system is installed in the track area and is supplied with the friction modifier through supply lines. The friction modifier is distributed over a total of 64 points in the brushes so that it is applied to the entire wheel circumference. The quantity distributed on the outer and inner side can be adjusted independently, as the outer braking elements brake approximately 20% stronger than the inner ones. Since a double-sided rail brake is used, the BrakeMaster is also built on both rails. The system is also equipped with sensors located in front of it in the rolling direction. They recognize the wagons rolling downward and the system starts to work. The friction modifier is pumped from the system cabinet to the brushes. The passing wheels pick up the friction modifier via the wheel side surfaces and distribute it into the rail brake system onto the brake beams. Here we see a sectional view of the BrakeMaster structure to give you a better understanding of the system. At the bottom is the sleeper, followed by a ribbed plate where the rail runs in the center. On the left and right is the structure for the brush devices, similar to that of a guide rail. The wheel side surfaces vary in the gray dashed areas, depending on the sine wave of the wagon, design and wear of the wheels. The brushes can be adjusted in angle and length. The bristles reach into the clearance gauge to touch the wheels. Therefore, they are flexible enough to compensate for the different distances. In this way, the friction modifier can be applied to the desired location and screeching can be reduced or prevented. After being under development for nearly a year, we were able to launch the first BrakeMaster BR25 in August 2023 in Graz. Ever since then, we kept a close watch at the system's workings. Therefore, the data of the rail brake is evaluated at regular intervals joined by noise measurements. These lasting measurements are made possible through the acoustic train monitoring system. This is not a standardized procedure, but rather relative noise measurements with a comparison between intervals. The acoustic train monitoring system is, by the way, not exclusively usable for our rail lubrication systems, but for all noise-reducing measures in general. The recorded data is evaluated and then shown using various sets of criteria. Take this diagram, for example. Here you can see the relation of recordings, including screeching noise and those that do not after the BrakeMaster's launch. The blue bars show all the recordings without any screeching noise, whereas the red ones signify screeching. Each group represents one evaluated hour of time. The orange line shows the relative portion of screeching recordings, and the green dotted line shows the linear trend. Judging through this evaluation, we can see that in the beginning, nearly 35% of all the recordings showed screeching noises. After 2 days of using the BrakeMaster, this was reduced down to only 15% of recordings showing screeching noises. Furthermore, we were able to prove a measurable reducing of length and volume of any screeching. In conclusion, we were more than happy with the BrakeMaster's performance so far and looking forward to improving it even further in the future. I would like to end my presentation with a quote and thank you for your attention.
Perfect. Thank you, Manuel, for your interesting presentation. You showed us first to summarize a little bit possible solutions for noise reduction. Of course, we know that noise barriers have the best impact on this topic, but there are other possibilities, for example, lubrication or conditioning of the rails, which may also give an additional value of noise reduction. In the final presentation, you gave us a closer look to the new beam rail brakes, which are installed first as a prototype now in the Graz shunting yard, giving the possibility to reduce the noise squeaking, and therefore special BrakeMaster system with friction modifier are used. So I'm very happy with your presentation, and I'm looking forward to some questions coming from the audience. I have nothing in the chat so far, so please feel free to give a hand or to show up your hand if you want to raise a question, and I will forward it to you. The field is yours. So I see that everyone is still thinking about good questions. I would like to start probably with as an icebreaker with the first question, Manuel. We know that braking wagons is a quite difficult thing. It is very difficult if we lubricate the rails on the top, and if you do some braking and you probably overrun the red signal. So how is it guaranteed that with this kind of construction, we do not bring any lubricant on the top of the rail, so that you may become a problem with the rail grip between rail and wheel, and not to overrun a red signal?
Yes, it is important there are two different kinds. We have on the one hand, here for the rail flank, we use a grease to reduce the friction coefficient near to zero, to reduce the noise and the wear. But it's important that this grease don't get on the top of the rail. For the top of the rail, for this case here, to reduce the noise, we use a friction modifier. This is a different material, and the friction modifier keeps the friction coefficient. It's similar to a rainy day when the rail is wet. It's a little bit reduced comparing to a dry rail, but it's above a border that the train can still brake. That's very important. And the same is here done at the rail brake. We use also the friction modifier here. If the friction modifier gets here on the top of the rail, it's the same for the top of rail conditioning. The friction coefficient is kept, and we can ensure that the train can brake.
So this was one of the questions coming from the chat now. Mr. von Bahn was asking what type of lubricants or the modifier are used and how environmental friendly are they?
Yes, that's an important topic. We have two types. The one is a grease, and it's completely biodegradable, and the other is a friction modifier, and it's also biodegradable. It's that's important actually in this time. So yeah.
Okay, so no big environmental impact by using different kinds of lubrication systems.
Yes, that's an important point, and there is no problem for the environment. Yes.
Okay, so in any case of noise squeezing or squeaking by using this kind of shunting components like this braking systems, I think your solution gives a big opportunity to reduce the noise. If you are not able, for example, to implement a new noise barrier close to the track, it is probably for the future a good and new solution to reduce noise problems in this area of shunting yards. So
Yes.
another question has arisen. Is there any specific distance for rail brakes and friction modifier systems? And how does this affect the friction?
No, yeah, there is no specific distance. It's the same friction modifier is used for both systems, so it's not a problem to combine that. And if there would be pumped too much friction modifier at the rail, cannot be a problem because it's thrown away from the train because the wheel can't take too much friction modifier and distribute it.
Okay, that means when the wheel is passing these brushes, the conditioning lubrication will be applied on the side faces on both sides of the wheel. And when the wheel passes this brake, and when the brake starts to push the brakes together, this special braking system takes over the conditioning and therefore reduces the friction between the wheel and the steel bars, and with an effect to reduce the noise.
Correct.
Okay.
Correct.
We have a question: how does this kind of rail braking system is in comparison with rail dampers? I do not know if you know rail dampers. This Retarderbremsen
Okay.
in Germany, which we use also in shunting yards, where you have
Yes.
every 60 centimeters a hydraulic cylinder,
Yeah.
which reduces the speed.
The Doughty retarders, yeah.
The Doughty
I
retarders.
know, yeah.
Is there any is it more efficient than a rail damper, this kind of braking system? I think I can answer the question myself. It is more or less the same. It gives the same. It is also able to reduce the speed to a certain amount which you want to achieve. When you're using rail dampers, you have this tuck, 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 this noise over the whole length of the dampers, and this is sometimes hundreds of meters of length. And in this case, with this brake, it is only on a short distance of 20 meters of length of this braking system, where you have the concentration of the noise and not in 100 meters away of the track.
And there is one difference if we want to condition or lubricate the rail or wheel. In this case here with the rail brake system, we had to conditioning the side surfaces of the wheel, and for the Doughty retarder, we had to lubricate the bottom or the circumference of the wheel. It's another point at the wheel. Yeah.
I received a question about how sufficient this lubricant works in the summer and how long can it remain on the rail?
Yeah. It's you can use it from minus 30 degrees to plus 120 degrees. So it's not important if it's summer or winter, that's not the problem. And yeah, if it's rainy, if it's heavy rainy, then it's washed away from the rail or from the bristles. And it takes approx 2 days that it's completely distributed again to reduce the noise.
Okay. I received now a question to myself about my point of view as a technician. If I'm happy with this kind of systems in the track, of course I'm not very happy with these systems, but I think for the shunting issues, for delaying, or if you have long distance freight trains and you have to separate it, several vehicles to several trains, it is a very efficient way without running with a diesel locomotive the whole day and to put each single way from one track to the other one to build a new train which runs in another direction. So of course I'm not really happy with this with this solution because of the noise problems. It's not a problem from the superstructure point of view. So the rail wear or the wear of the components like sleeper or ballast is not really an issue because you are running only with low speed over this kind of installation. But I think from the efficiency for freight trains to be detached and attached, it is the most efficient way how to do it now. Probably in the future when we have coupling systems in the middle, automatic coupling systems, where you do not need manual input to attach or detach vehicles, or if we have robots instead of big locomotives to move vehicles on the track, probably in the future it will be no more necessary to have this kind of shunting equipment. But I think at the moment we do not have really alternatives to it. And if it is a retarder, as also a Dauti retarder system, or if it is such kind of beam braking systems, I think it's only not really of importance. Another question, what are friction modifier brushes made of? Is it of plastic or is it of steel or something like this?
It's a kind of plastic. Yeah.
And you have small pipes coming in certain,
Yes,
every 30 centimeters or something like this?
correct. You can see it here on the right picture. The white is the brushes with the several bristles. It's like cables with 1 millimeter diameter. And here the black tubes coming out the friction modifier. That's the supply lines for the friction modifier. And you have it every 20 centimeters approx over a distance of 2 meters. Yeah.
So after 1 or 2 weeks, the whole brushes are full of this conditioning material, and it should be
Correct.
possible to apply this kind of conditioning material to the side of the wheels on both sides, on the left and on the right hand side. Yeah.
Yes, correct.
Perfect. Another question is, does it increase costs, rail and wheel maintenance, by using this application?
Yes, the system itself costs a little bit. Yeah, that's the one. In fact, not really. I see the thing is that we don't have too much experience right now. The system is nearly a year installed here at this place. It's the first of this type. We know it from other systems like the rail lubrication systems for the front lubrication or the top of rail, that we can extend the lifetime from the rail. That's what we know. In this case, if it has an impact on the rail brake systems, we doesn't know right now.
Okay. So I think there are not really costs for the rails because there is not really an issue, an impact on the rails. It is only a measure to reduce the noise, the squeaking noise, this very high frequency noise when the brakes press together and steel comes together and makes this noise between wheel and then this beam brakes. That's the only reason why we install this kind of device. And that it does not really affect the rails and the wear of the rails. But of course, if you do some top of rail lubrication, I think there are experiences that you can reduce also the rail wear on the head, on the rail heads, especially in corrugated rails, by using this kind of top of rail lubrication. Not only reduce the noise as the special squeak in curves, in very narrow curves, but the second effect is also a small reduction in railhead wear by using a top of rail lubrication.
Yes.
Well, I hope we have asked I think another question arose dealing with the assumption was, does the plastic cause wheel wear in long term that increase maintenance? I think these brushes are like the brush you use in the household when you are cleaning the floor or something like this. So it is very flexible, so it does not harm the steel, the wheels coming from steel material. It is yeah. When I'm sorry, you have no picture when a wheel passes this
No. Just this
these
technical.
brushes, but they are like a toothbrush or like a brush in where you clean the floor. It is very flexible, and you have no problem with wear on the wheel.
Correct. Correct.
Steel,
Yeah.
steel is much stiffer than plastic.
Yes. Yes. And we have also no wear on the bristles itself.
Yeah.
Yeah.
But I think, Manuel, if someone is interested in this kind of techniques, top of rail or flank lubrication, they can go to your website and have a quick look at it, get some information how it works, or get directly in contact with you to get further informations or details or reports,
Of course.
research reports on how this affects noise and then thank you very much for this first presentation. Once again, Manuel, I would now like to go to the second presentation. If someone still has a question, no problem. At the end of the second presentation, I will give you another possibility to ask additional questions to Manuel. I would now let me hand over to our second speaker, Mr. Günther Ax. He's managing partner and engineering consultant by FCP company in Austria. He will talk about ground-borne noise and vibration reduction in urban areas. So Mr. Ax was born in 1979. He's the managing director and a graduated consulting engineer for civil engineering at this FCP company. He has a civil engineering degree from the Technical University of Vienna and made a PhD program in engineering sciences. and also is court certified expert for noise and vibrations. Since 2005, he started a career at FCP in this company and made already numerous railway projects, not only in Europe and especially in Austria, but also in Asia, Africa, Australia, and South America. He's member of certain standardization institutes and also member of the Science Advisory Board of the Austrian Society for Earthquake Engineering and Structural Dynamics. So I want to give you the floor, Günther, and I'm looking forward to your presentation.
Thank you very much, Bernhard. I hope you can hear me.
Yeah, perfect.
So I will try to share my screen. Okay. Thank you very much for inviting me for this lecture. I'm very honored to be allowed to give a presentation on a slightly different topic than the topic before. I will talk about ground-borne noise and vibration reduction in urban areas, meaning that I will not talk about airborne noise. I will talk about the vibration that are generated in the track, transferred to the buildings, and that vibrations are generating ground-borne, so-called ground-borne noise, which is the rumbling that you can hear when you are in a building above a metro line, for instance. So first of all, I will give you a very brief introduction to our company. We are an engineering office and consultant office with our headquarters in Vienna. We have about 350 staff members. We have several branch offices, mainly in Europe, and we are active in the whole area of civil engineering, but with a special focus in track engineering and noise and vibration engineering and assessment in the railway field, let's say. Yeah, we were founded in the 1960s, so it's a rather experienced and old company. As I already mentioned, we have 315 employees, and you probably have heard about VC. This is our sister company, which was founded in 1968. We are working with both companies. VC is acting more internationally. So I will start with the topic itself, and I will start with a question: why is it important to have ground-borne noise and assessment or ground-borne noise and vibration assessment in urban areas? So one of the main topics, or one of the main reasons, is we want to avoid the annoyance of residents due to the noise and vibration impacts. We want to protect sensitive receivers among all the residents in the buildings. We also have sensitive equipment, for example, of hospitals or laboratories. Of course, we also want to protect the cultural heritage and the monuments, which we have very often in urban areas, such as churches, mosques, and so on. And one of the most important things is we want to increase the acceptance of public transport, and this particularly in the urban areas. And how is the ground-borne noise and vibration assessment done? In a very principal view, let's say, we need to define the limit criteria, which is different to many countries. It's not the same used worldwide. And we have different limit criteria for humans in the buildings, for historic objects, and for sensitive equipment. Then in the next step, we assess and evaluate the future noise and vibration impact if limits are exceeded. In the next step, we select suitable mitigation measures. We do a dynamic design if it's track-related mitigation measure, and we verify the effectiveness of the system. So in a very general picture, you can see here, this can be a main line or a metro line in an urban area. What you can see here is that the vibrations are generated in the rail wheel interface, in the tunnel in this case. They are then transferred via the subsoil to the foundations. There is a transfer from the subsoil to the foundations, and then the vibrations are generated within the buildings, and they are amplified or reduced depending on the structural dynamics of the building itself. And then you can feel and hear these vibrations or the ground-borne noise in a certain room or in a certain flat within or inside this building. The main difference now between ground-borne noise and vibration assessment and airborne noise assessment is that our medium, where the vibrations are transferred or the waves are transferred is very inhomogeneous. It's soil, it's layered soil very often, and it varies with along the alignment of the railway track. So this makes it a little bit more difficult, or at least it needs more attention on the transfer medium from the source to the impact. And the basic requirements for a reliable noise and vibration assessment is, first of all, of course, we need an accepted methodology. Today, I will focus on an internationally used methodology. This is the FDA method. Basically, it comes from the USA. It's the Federal Transport Assessment method. Then you, of course, need to consider all the sensitive receivers, including their structural dynamics, their structural behavior, and the building use. So we differ then between, for instance, residential buildings and office buildings. In the next step, we need to very accurately think about the vibration emission, the so-called source, the train train running on the rails, and the vibration transfer, which needs to be determined according to the local conditions. As I already mentioned, it's not a homogeneous medium, so it needs to be done very accurately. The noise and vibration prediction needs to be performed in frequency domain. This is very important. A single value prediction is not sufficient to select a proper vibration mitigation measure. This is simply because we have very different dynamic behavior in the buildings along the track alignment, and it's not sufficient to only have a single value prediction. In the next step, if it's necessary, the mitigation measures needs to be selected according to the results for each relevant sensitive receivers. So it's then it's clustered into a section-wise selection of optimized mitigation measures. We will see that later. And the method and each step of the prediction needs to be comprehensible. This is very important. I have now clustered the next slides according to the methodology of the FDA. What is very special in this methodology is that we have a first step before we start with the methodology. We have a so-called early identification of sections without mitigation measures. And why is that important? We very often were called during the tender stage of a project. And during a tender stage, you very often do not have much information about your project itself. You have to base your first indication where you would need or probably need mitigation measures on a very rough prediction. And this is very well described in the FDA manual. And therefore, I think it's important now also to present you this first step. The next steps are, as I already mentioned, we need to determine the sensitive receivers. There are different building uses, residential buildings, as I already mentioned, or offices, or hospitals, schools, and so on. Then we need measurement of the vibration emission of the excitation source. I've written here measurements because there is a very, very large scatter of the vibration emissions of the vibration source. So the first selection I would always take is to measure the vibrations. If this is not possible due to several reasons, due to probably the train is not existing in this country or in this urban area, then as a second option, I would model this and simulate it. But in a first step, I would always try to measure the vibration source. Then we need the vibration transmission through the track system and to the tunnel and the soil and rock subsoil. There, as I already said, we will cluster due to the soil conditions. Then we have the vibration transmissions through the buildings along the track. I will explain that also later. And then the sixth step is the prediction and verification of the ground-borne noise and the vibration limits inside the buildings. So if we have an exceedance of the vibration limits or the ground-borne noise limits, we will then introduce a mitigation system, for instance, a track-related mitigation system, and the whole prediction will be done again as long as we meet the limits inside the sensitive receivers. And finally, a proper mitigation system, proper mitigation measure needs to be selected, and also the extent of the mitigation system needs to be selected very well. So coming now to these steps, I will start with the early identification. I already mentioned that it's very important in the tender stage. FDA manual gives a very good indication based on distances from the track system. If the distance of the sensitive receiver is inside or outside a certain limit, let's say, it's probably affected for vibrations and ground-borne noise. So this can give a very early indication for areas that are non-sensitive for vibrations and ground-borne noise. And this is important in the tender stage because, as you can imagine, if somebody want to select a mitigation system, we need a certain height, a certain geometry in the track. And if the geometry of the track increases due to the mitigation system, then we might need a larger tunnel diameter. And this is a very cost-effective decision, and this needs to be decided very early in the project. Therefore, this is a very good method to give an indication of how much geometry or how much space would we need, or even will we need mitigation systems in certain sections. So in the next step, as I described already, we will really determine every sensitive receiver along the track route. There are certain rules. For instance, 70 meter left and right of a tunnel section, you need to really select and determine all the sensitive receivers that you have there. This is important because the sensitive receivers can vary. And if you have a guiding sensitive receiver within one section, it really can dominate the selection of the mitigation system. So it's necessary to go outside into the field and do a collection of the sensitive receivers. Here I have an example of how this could look like. You can have a record sheet where you have the most important quantities of a building, such as the span width of the ceilings or the material of the building. The purpose of this determination of the sensitive receivers is to get an impression of how vibration prone your sensitive receivers along the track alignment are. So the next step is the determination or the measurement of the vibration source. I've given you here an example of a vibration source. It's a vibration spectra. You can see here the frequencies from 6 to 250 hertz. This is the main dominating frequency for an urban metro system, for instance. And as you can see here, we have here recorded measurements for a very long distance. It's just one type of trains, but several different train sets. And you can see that the scatter is really high. So if somebody would go out into the field and measure only 2 or 3 different trains of one train fleet, it's probably not a good idea, because it can happen that you measure trains in a very good condition, and then you underestimate your vibration and ground-borne noise assessment. So it really should be a large number of train pass-bys, and we recommend then not to take an average value, but at least to take a 90 or 95% fractile value, so that in future you will not have problems with your train fleet in an average maintenance conditions, let's say. The next step then is to verify the geotechnics along your track alignment. So as I already mentioned, this is a real case of a metro system in an urban area. You have layers of subsoil. The layers are not straight, as you probably know. They are very different within your urban area or your track route. So what we are usually doing is we find homogeneous sections. This can be 100 meters, but it also can be 1 kilometer if there is a really homogeneous section. And for these homogeneous sections, we either do measurements or numerical simulations. which I want to describe on the next slide. So if you have the possibility, if there is already a tunnel section where you can do measurements of your vibration transfer, I would really recommend to measure the transfer from the tunnel to the surface, or from the tunnel to a sensitive receiver, because it gives you more accurate results. It gives you the real values from the section that you want to consider. And what is done here is that we are doing impacts along your track route. The impacts are set at the positions of your track axles, or at the positions of your bogies, and they are then integrated over the length, and they give you a transfer function from the tunnel to the surface. What is very important is that FDA manual is not using only transfer functions and vibration spectra. They're using force density spectra and vibration transmissibility, which is more or less, it's not completely independent, but it's very independent of the track system then. If it's not possible to measure the vibration transfer, of course, it's also possible to make simulations. There are various programs where you can simulate the vibration transfer from your tunnel to the surface or to a sensitive receivers. It's just simply you have a lot more boundary conditions and a lot more uncertainties compared to a measurement. So you have to be aware of that, and you have to be aware that probably your safety factor needs to be adjusted to the input data that you receive from your client or from your project. But the thing is that in a very early stage, of course, you do not have a tunnel in your project, because it's just very early stage or tender stage, and in this case you only can simulate the transfer of your vibrations in the subsoil. Then the next step, as I already mentioned before, is the vibration transfer through the buildings. This is a very important step. You have, as you can see here on these different pictures, very important buildings in an urban area. You have modern ones, you have high-rise buildings, you have residential buildings. So it's not possible. This is just from practical experience. It's not possible to measure every building. But what you can do is you are clustering different buildings and try to get an indication of how the vibration transfer within the building is amplified or reduced. And for instance, in this case, we did this for 7 different building clusters, let's say. And based on that, every sensitive receiver along the track alignment is then applied with a vibration transfer. And if you have done all these steps, you can then combine all these elements into a ground-borne noise and vibration assessment. As I already mentioned before, I would not use a single value analysis. You can see here all these different elements are depending on the frequency. So everything that we determined before is frequency dependent. And if you combine it, then you get also an impact spectrum. And then you can see which frequency is dominating your vibration response or your ground-borne noise response. And you can really do a tailor-made mitigation measure, which then reduces really the frequencies that need to be reduced. So it's not the structural dynamics has a great disadvantage. There is no safe side, so it's not possible to just simply say we will do the most expensive vibration mitigation system on the track, because it can happen that exactly this mitigation system is not proper for your impacts in a certain building. So this is done, as I already said, for every sensitive receiver along the route, and there can be a lot of them. You will not really be able to read these numbers, but it's not important. Every line you can see here is a sensitive receiver, and on the right-hand side of this table, you see vibrations and ground-borne noise. So usually we are always checking both impacts, vibrations and ground-borne noise, because it can happen that one of those two impacts are exceeding the limits, or both are exceeding the limits, and then you need to introduce mitigation measures. And you see then in these tables how these mitigation measures are affecting your impacts again. So it's possible, for instance, that you are exceeding your ground bond noise impact and your vibration are below the limits. Then you are introducing a mitigation system, and then it can be opposite. So it's really a step-by-step assessment where you need to carefully select mitigation measures, and finally they need to fulfill, of course, both limits inside the buildings. This is an example how this can look like. In the end, we have an urban area. We have a track route that is aligned through or below buildings in a tunnel section. And as you can see here, there are certain sections where you need a mitigation measure. In this example here, a mass spring system. And you also have sections where you do not need any additional mitigation systems. And this is due to the effects that I explained before. There are several elements. Either you have a better transfer in your subsoil, or you have really residential buildings with which are very vibration prone in these sections. So it just needs a really careful selection of the vibration system and the extent of the vibration system. Yeah, this is the summary of all the elements that I explained before. What is important on this slide is we always have a safety factor on the vibration and ground bond noise assessment, but the safety factor is not the same for each project. So if you have a project where your input data are very vague and you have not very detailed information, it's recommended to increase the safety factor. As a limit, let's say on the lower bound, I always would introduce a safety factor of 3 dB. But we also had projects in the past where 10 or more dB were introduced as a safety factor. So now I want to briefly go to some of the measures to reduce ground bond noise and vibration impacts. And first of all, I have a very general slide where you can see the different types of vibration mitigation measures on the track. I only now will focus this presentation on the track side mitigation measures. There are also mitigation measures that can protect your buildings. You can have elastically layered buildings, and you can also have vibration mitigation measures in your transfer path. For instance, a trench in your subsoil. But I would say the most important mitigation measures are trackside related mitigation measures. And what you can see here is that there are different types of mitigation measures. Some of them are more effective and some of them are not that effective, and they are here coupled with the costs. Just to give you an indication of, it's unfortunately it's not that the most effective vibration mitigation system is the low cost system. But yeah, you can just simply choose your mitigation system according to the needs that you have in your vibration and ground bond noise assessment. And I will now focus on the next slide to mass spring systems. I'm pretty sure that you are aware of what I'm talking about. Mass spring systems are elastically layered track structures. And what is important is they need to be designed in two different ways. There is a dynamic design and a structural design, and a very strong interaction in between those two designs. The dynamic design is described by the needs that you have based on your dynamic or your vibration and ground bond noise assessment. Based on that, you get an insertion loss, which is describing the effectiveness of your system. And based on the insertion loss, you can choose a dynamic system that is able to reduce your vibrations so that you can meet your limits. But it's not only that, you also need to select a suitable elastic element. There are different elastic elements on the market, and the most important thing is you need to coordinate with the structural design, because as I already mentioned, in most of the cases you have a tunnel with an available space, and you need to design your mitigation system so it meets the available space. There's a possible height that you can use, and there are also maintenance issues that very often guide the selection of the mitigation system. Then you have different loads. You have the vertical loads coming from your train and the lateral loads, but you also have temperature and so on. And there are very often maximum tolerable deflections. For mitigation systems, we are always talking about elasticity. So your track will have deflections more than your standard track. And to avoid that the vehicle dynamics is out of your limits, let's say, you need to keep this maximum tolerable deflections. And the subgrade, of course, is also important for the structural design. And those two different designs, let's say, they need to be strongly coordinated and interacted. So I just want to go very briefly about the different types of mass spring system. You maybe have heard already about the mass spring system with point bearings and with full surface bearings. There is a system that is in between those two types. This is a mass spring system with strip bearings. But the most common ones are either point bearings or full surface bearings. Point bearings in general are more effective, but it's of course depending on the mass of the trough that you are that is basing on your point bearings. They have advantages and disadvantages. You have a remaining space below your track, which is sometimes problematic, and some clients they have the need to inspect the bearings, and also there is sometimes the need to replace the bearings. So in this field, let's say you have different different needs from your clients that needs to be considered in the selection of the mitigation system, in the mass spring system. Here are some examples. This is the mass spring system from the Vienna transport system, the metro system. They are using a mass spring system with a natural frequency of 21 Hertz, a full surface bearing. What is interesting on this sketch here is in the middle, in the center of the track axis, you have a drainage. And this is very important because you always have water in your tunnels due to washing or different reasons why you can have water in your tunnel. And there is the need that this water that can also come into your elastic layer can be drained below. And this is really important to be considered in the design in a very early stage of the design. Here is a different example from a system with point bearings. You can see here on these pictures on the right side that there are manholes. There are different reasons for these manholes for the point bearings. First of all, the point bearings at these projects, they were installed after casting the concrete. So the concrete was casted on the subgrade or on the base concrete. And then the mass spring system is checked up with hydraulics checks. And the elastic elements are then installed from these manholes. And the second reason is that if a client really wants to have the possibility to replace these bearings, this can also be done from these manholes. And the last example I wanted to show you is a light drum system, also here from Vienna. You can see here also a fully full elastic layer. What is interesting at least in Vienna, is that Vienna public transport systems usually are installing their mass spring system during the regular operation. You can see this on the right top picture. So this train is really running on an open track, let's say. You have supports below your rails, and they are casting the mass spring system step by step. So they are only reducing the speed. And during the regular operation, a completely new mass spring system is installed. This is very special, and I would say it is a particular need of the client here in Vienna. Yeah, so I hope I could give you an overview of ground-borne noise and vibration methods, protections, and assessments and mitigation systems. As Bernhard already mentioned, we have done this assessment worldwide, so it's not only standard in Europe. There are a lot of projects that we have done in Asia, and they are all using the same method, let's say, or basically the same method. So if you want to know more about different projects or different steps of this methodology, please feel free to ask either questions or to contact me. Thank you very much.
Thank you, Günther, for your very impressive presentation. You gave us a perfect overview of the different steps in the process of ground-borne vibration assessment with very practical examples. And you could show us also the different possibilities for possible measures to do ground-borne vibration mitigation measures depending on costs, of course, and the effectiveness. And finally, you were focused on special mass spring systems in several examples from metro or tram systems, which gave us, I think, a very good overview how the process and how the whole assessment is done. And I would now kindly ask our participants in the web to raise questions to Günther or write it down in the chat, and I will translate it to him. So please feel free to ask questions to him. You can do it live. You can raise your hand and I will give you the floor. So Mr. Gunacker, Manuel wants to ask something. I give you the floor, please, Manuel. Nothing? Okay. Then I have to look who else will raise a question. So one arrived me by chat. The question was if I understand mass spring system is more effective for tracks with heavier axle load. This is the question.
I think this cannot be generalized. What I mentioned is that mass spring system with higher mass they can be more effective. This is correct, but it's always a combination of the spring damper system and the mass. So and you have to consider that axle load is not the only load that you have on your elastic element. You have, of course, dead load, basically your trough, your concrete slab that is based on your elastic element. Yeah, so I would say it's not generalized. We very often have mass spring system for metro systems because, of course, they are in the urban areas. And when you have heavy haul systems outside urban areas, you most probably will not need mass spring systems.
Okay, I hope this could catch your question. Anyone else who want to ask something?
Yes, please. I was going to ask a couple of questions. Does which type of ground-borne frequency creates the most complaints and do people find most disturbing? Is that the higher frequency or the lower frequency? And I was wondering which travels further in the ground. And the second question is about the design life of the mass spring bearings, please.
Yeah, the first question. There is a dominating frequency that we can see very often in metro systems, which is around 50 to 80 hertz. This is coming from the source. So the train very often generates vibrations in this range, let's say. The thing is that most of the people, and I include myself, we are not able to differ between vibrations and ground-borne noise. There is not a sharp, let's say, border where you feel vibrations and where you feel ground-borne noise. What is very, very uncomfortable is the very low vibrations from 4, 5, 6 hertz. And you can, if you think of seasickness, you can imagine at these very low vibrations, you get sick, let's say, because your inner organs, they are they're getting in resonance, and this is very uncomfortable. But most of the time, what we have in urban areas, we can see that these frequencies between 50, 60, 70, 80 hertz, they are the frequencies that we need to eliminate, let's say. And which is traveling further. This is really strongly depending on your soil. If you have rock, the higher frequency is traveling, is traveling better. If you have a softer soil, it can also happen that lower frequency is traveling through your soil. So this is always depending on which type of soil you have. And your last question, I forgot now. Sorry.
So thank you. It was about what's the design life of the mass spring
the design
bearings?
life,
yeah. How often do they need replacing?
Actually, we have never replaced one.
Okay, right.
But your question is really very important, because we're discussing this every time in a project. I would say that the design life varies from the clients between 50 and 100 years. So they try to get a guarantee that the system is working for this time. But we have mass spring systems that are working for 50 years and more, and we have the same effectiveness than they was installed at this time. So we really have a long time experience of mass spring systems, and there is no decrease in effectiveness. So we will of course monitor this also in future, but currently there is no indication that there is any loss in effectiveness for the standard materials, at least. Of course, there were some materials in the past that were not long lasting, but they are not used anymore.
Okay, thank you. Thanks.
Thank you, Günther. I received a question via the chat. The question is, does point spring systems is more reasonable in light tracks? Question mark. As a whole, what was the difference of point spring with the whole mass spring system besides the costs? What was your experience on using both systems? So what is the difference on point spring systems and?
Yeah, there's one maybe important thing that I skipped during my presentation. What is a very big advantage for strip bearings with filler material or for full surface bearing is the construction phase. If you can imagine, if you put a layer on your sub concrete, you can directly pour your concrete on this mat. So this is a very big advantage. If you have point bearings, you either need to check them up, or you have to use some different types of concrete, precast concrete elements that are put on your point bearings. This is one of the things that I want to mention that makes it sometimes difficult to install point bearings. And the second thing is we have done some analysis that the durability of the system is a little bit decreased if you would use point bearings. This is because the bending in your concrete slab increases, of course. It's like a bridge on piers if you base it on point bearings. So the durability of the concrete slab itself can decrease if you use point bearings. So there are some certain aspects. This is, of course, depending on the available geometry and the available space that you have in your tunnel. So it's not that there is no rule of thumb that you can use point bearings in urban areas and they are always better. So unfortunately, this is not the case.
I hope this could answer your question. I received from Stefan Bonban the question that the experience of him is that the tailored approach for every project takes a lot of time. Amongst other things, specific approvals are necessary. And the question is now, what is your opinion on a standardized portfolio of mass spring system with a general approval, e.g. from German EBA? Do you think this could be helpful to be quicker in the execution of mass spring projects?
Yeah, I think we need to do more research on that. Of course, we had this discussion already before, and we know that it takes time, but in most of the cases, it's very important. But if we are talking now about dB, I mean, my presentation now was focusing on urban areas. Urban areas are very special because you have a lot of buildings. You have not only residential buildings, you also have sensitive equipment. So in urban areas, I would not recommend to use from the shelf or off the shelf product or systems, let's say, because at least it's necessary to know your area where you want to build your track route. But for I understand Stefan von Bund's questions, and I think in future maybe there will be a possibility to think of these solutions.
Okay, thank you. I have another question. Thank you for a great presentation, Christopher said, especially on this FTA methodology when conducting propagation tests to characterize the surrounding geology. The question is, so do you also include interior measurements to characterize the coupling and propagation into typical building types, or do you find variability from building to building too high, e.g., maybe better to rely on typical literature factors instead?
Very good question. No, if it's possible, we prefer to also place sensors inside the buildings. The picture that I shown you is from an area where we did not have sensitive receivers directly at the track. Therefore, we put it on the surface. But this the transfer from the soil to the buildings, you have a lot of literature factors, but of course it can vary. It's depending on the foundation type, if you have pile foundation or flat foundations. So if you can increase your set of measurements and you can increase your measurements for the prediction chain, I would always recommend to do measurements instead of using literature factors.
Okay, I hope this could answer your questions. I have received no further questions so far. So if there's anyone, please announce. Otherwise, I would, yes, please.
I have a question. Question is regarding mass spring system for tramways. So I work on the market in the Netherlands, and I often get the question, how is the influence of the stiffness of the subsoil in the meaning of mass spring systems for tramways? It's clear, it's stiffer the better, but yeah, is there any other things which has to be taken in consideration?
There is, of course, an influence, as you already mentioned, and we are recommending, at least we are doing that in Vienna, to always do also soil investigation, soil measurements before we are designing the mass spring system. So there is, of course, the effect that the stiffer the direct subgrade below your elastic layer is, the better it works. You also have this effect at subballast mets, but also that the subsoil below the subgrade, let's say, can influence the effectiveness of the mitigation system. It's like a set of spring in a serial that would negatively influence the mitigation effectiveness of your mass spring system, for instance. So it can happen that during the design of a mass spring system, also the subgrade is upgraded, let's say.
Okay.
Okay, thank you very much, Mike. So if we run out of questions, then I would finally give you the floor if there are any general questions also related to Manuel Gunacker's presentation first. Another question from Luis arrived now for Günther. how should other vibration sources be detected and eliminated when measuring inside buildings?
Yeah, very good. This happens very often. We very often have other sources when we are measuring inside buildings. So either you need to be aware that they are existing, and what can happen is that measurements are very often done during the night hours, where other sources are at least reduced to a minimum. But what is really important, and we discussed this even yesterday, is we have a lot of sensitive receivers with very low limits. Basically, this laboratory and fabrics sometimes have very low limits, and then it can happen that you can manage your vibration from the track, but you have other sources that are guiding your vibrations inside the building. So it's very it will be very wise to explain your clients that track related vibrations is not the only source where your vibration impact can come from.
Okay, thank you very much. I hope this answers these questions. So last chance for a question for someone in the audience. One question arised. Thanks, Günther, for a great presentation. There was a question now coming from Uganda, from Africa. He said that especially for Africa, these topics are definitely of high interest, even for the African railways, and he is very thankful that you could give this kind of information. And I think this is what even UEEIV is trying to build up, to be a platform to share knowledge between engineers, between railway engineers, and if it is possible with this kind of railway talks to bring more light in, of course, only a small amount of certain topics, I think then we can fulfill the requirements from ourselves. So I would finally thanks once again to Manuel Gunacker for his presentation on ground band vibration in shunting yards and the solutions, possible solution with the top of rail lubrication systems or flange lubrication systems. And I also ask thanks to Günther talking to us about the assessment of ground band vibrations. I would like in the final end make a short announcement on the next railway talks to you. I share my screen with you. For all who think that this kind of railway talk is of interest, I can announce the next and even 7th railway talk will take place on 11th of September. The topic will be related to ballastless track systems and technologies. We have already one speaker from Borne company, which will give us an overview on slab track systems in various countries and their experience about it. And I think we will find also a second or probably a third speaker for this railway talk. So please put it in your note, in your books. 11th of September will be the next railway talk, hosted by the Union of European Railway Engineering Associations. And for those who are interested in joining our railway forum in Sofia, it will take place on 8th and 9th of November. And the topic will be the future of railway interoperability. So 25 years now of experience and innovative strategies with TSIs. So we know that European Commission and ERA has started a very ambitious project 25 years ago to harmonize the railway system in Europe. And we want to give you in this seminar live in Sofia some presentations from politicians, but also from engineers, how far this process has now already been developed. Where do we stand now? What will be in the future? Where is the railway interoperability going to? And we will make a wide span topics, not only covering the TSI specifics, but also discussing a little bit about ETCS. We want to talk about night trains and train operation in the future, and also how to meet the expectations for sustainability, and also solutions to increase capacity on the railway lines. So it will be a broad topic to be discussed, and whoever is interested in this seminar, please register on our website, www.ueiv.eu. We will give you the opportunity to subscribe within the next days. So it's not available at the day today, but in the next days you will be able to participate on this or to subscribe to this railway forum in Sofia. So thanks for today's railway talk. I hope we met your expectations. We gave you some important or interesting informations. I would like to say thanks to the audience, to you, also for raising questions. And I would be pleased to welcome you next time in September for our next railway talk. Bye-bye to you. You will find the whole presentations in a few days on our website at UEEIV, and also find the presentation. It was recorded with cameras, so you can follow this presentation again whenever you want in the next days. So bye-bye for now, and see you next time. Bye-bye.